So we are R3 machine learning across wireless networks. I'm Akshar.
And I'm Kirthana.
I'm Varun.
So a quick project introduction for us. A lot of devices and computers and cars and phones in general will be wanting to use AI applications in the future. But the problem is these are kind of smaller devices, so they don't have the computational power to run a lot of these AI applications. So often they'll leverage the cloud and use the cloud to help them with this. But this causes a lot of problems such as delay and privacy concerns and security.
Yeah, so a potential application of our project are security systems. So currently security systems use some sort of object detection AI to determine whether there are threats in their field of vision. But currently they have to offload all of their image data to another server to determine whether or not there's a threat. And that can take a lot of time. So we could potentially use our application to load, miniature AI models, or at least a portion of them, onto our security camera for lower latency.
So our problem statement is, when should phones offload to the cloud and ask for help? So we would require a simple AI model and the strategies to offload and the network conditions, and then evaluate these results.
Right. So our AI model is just a basic neural network. And for you guys to know what a neural network is, basically it's inspired by the human brain's neurons. And so it has an input layer, and then it has a bunch of hidden layers in the middle, and then it has an output. So all you guys really need to know is that an input is fed in, it goes through a bunch of layers, and then an output is like a prediction or some sort of classification.
And the choice of model was ResNet 18. It's a very popular model available online, and it gave us an accuracy of around 92%. And the data set we used was a CFAR10 data set. It is also very commonly used in machine learning models, and it consists of 60,000 images, around 50,000 for training and 10,000 for testing the models. And both the CFAR10 data set and the model ResNet 18 are very common benchmarks in machine learning.
Yeah, so the core of our project is offloading. And essentially what that is we take our original AI model and we split it down the middle. And we put a portion of our AI model on our device and the other part on our cloud. So the device is going to be the entry point to the AI model, where it'll take in an image. And then after it finishes executing on its phone, it will then be offloaded to a computer. So early exiting is pretty similar to that, where the client model is, again, a portion of the full model, and so is the server-side model. And the client model will execute some sort of input, but after the client model finishes executing, it will then make a dynamic decision on whether or not to offload to the server to finish the rest of the model. So in our project, speed is also really important because we're transferring a lot of data between the client and server. So to make speed a priority, we used Python's fast API to communicate really quickly between our server and device. And we're also sending our data and tensors as buffer streams instead of the industry standard of JSON. And both of those combined increase our performance by over 100 times, which allow us to process 500 images per second over an Ethernet connection. So we realized that most networks are wireless, and we were testing with Ethernet. So we want to simulate how our connection and model would work in a Wi-Fi environment. So here we're in the bottom left, you can see that that's our Ethernet there, and you can basically see that without any network delay, our model is extremely fast. But as we add more and more network delay, simulating a weaker Wi-Fi network, the overall execution speed of our model increases pretty dramatically in a linear fashion. And this tells us that our model, although it's extremely fast, it's highly impacted by network delay. So network delay is a big bottleneck in our project.
Right. So for evaluation, we then had to construct an experiment and what we wanted to do with the computers that are available here is simulate a busy server and then evaluate the different strategies that clients could deal with that busy server. So this was the experiment we set up. We had multiple computers emulating different phones, and then we had one computer emulating the cloud or the server. And basically we'd have these multiple phone devices, we'd have them offload to the cloud. And from here, there could be two scenarios. So the first phone offloads to the cloud, and the second phone also tries to offload to the cloud, but the cloud is busy. So from here, scenario one is that it could it could go back to its own prediction on its second phone on its own device, or it could wait for the server, and it could basically wait for the server to finish processing phone one's process and then process the device two's request. So these two approaches, the second approach where you wait for the server obviously will have a slightly higher accuracy, whereas the other approach where you just go back to the smaller model on the device, that has a slight dip in accuracy. But what we found was that it saved a lot of time. So when we just went back to the client device's own AI model, it ran at about 1 minute 25 seconds, whereas waiting for the server took about 4 minutes.
Yeah, so it's just a demonstration of our product. So essentially we're feeding in an image to our AI model here, and you can see it correctly predicts the object and also tells us whether the image was offloaded or processed locally. So here, when we feed it an image of the horse, you can see that the confidence is pretty low at 60%, and so it offloaded to the server for improved accuracy. And you also notice that when we offload to the cloud, it doesn't take much more time than processing it locally.
And our conclusions from this project are, for a small dip in accuracy, we can get an increase in speed by offloading when needed. And applications may prioritize either accuracy or latency. So for example, if AI is being used in security camera footage, we prioritize accuracy. However, like if we need a quick decision, such as like a self-driving car determining whether to stop, we would prioritize latency over accuracy. And then the challenges we would encounter are managing multiple clients in real life, because at the end of the day, like in real life, we would be probably managing more than 2 clients. And then the model portability for micro devices, because our model is small, it's around 50 MB, but for very small devices such as doorbells, I think we would need an even smaller model. And performance in weak wireless connections. So poor performance would make offloading to the server much slower. And our future work consists of compressing and optimizing our models and exploring more dynamic thresholds. So just changing how confident we would need to be to offload to the server, and then training the model with more diverse data sets, such as like any other data sets such as CFAR10, because we were using CFAR10 for most of our training and testing, and investigating other types of models, because again, most of the work we were doing was with ResNet 18, and yeah, we would like to experiment with other types of models and generalize our model more. Thank you.
Thank you.